So welcome everybody, and so today at our analysis seminar we have Allan Sly from across the golf court, and he will talk about spread of infections in random walkers, which looks like a quite actual topic actually.
Yeah. So I mean, as some of you may be aware, there's a pandemic going on at the moment, and so this was sort of partly our sort of I don't know, sitting around talking on Zoom over the summer, sort of I guess pandemic themed research, but it goes back to, and we look at some problems that have been sort of generalizations of questions that Keston and Sidrovicius looked at, and so most of it will be about joint work with Duncan Doverne, who's a postdoc at Princeton, and but also I'll also mention some earlier work with Dor Ellenboim and Danny Nam, who are two students of mine. Okay, so you've probably heard like epidemiologists talk about the SIR model. This is sort of susceptible, infected, removed, or sometimes recovered, when they're talking about sort of the growth rate of infections. And so this is so I'll be talking about sort of an interacting particle system where we have a sort of sea of particles, each doing continuous time random walks. Initially, there's a sort of Poisson density lambda. So at each vertex, you have an independent Poisson mean lambda number of particles. And initially, they're all susceptible. And then we add one infected particle at the origin. And when an infected particle meets a susceptible one, then the susceptible one becomes infected. And the infections don't go on forever though, and so the infected particles will recover at some rate mu. And we want to understand, does the infection go on forever, at least with positive probability, but particularly if the recovery rate is small enough. And so this is sort of a simulation, and you sort of see, okay, the set of infected particles is growing, but it's sort of leaving behind a sort of empty disk where most of the particles, where it's mostly empty because those particles got infected, but then recovered, and so we've removed them from the picture. Okay, so this
is this how they connected to each other? How do they interact?
So the black particles are the susceptible ones, and the red ones are the infected ones. And just if an infected particle and a susceptible particle are on the same vertex, then the susceptible one becomes infected.
Okay, but I guess this picture's in the plane, or I'm a bit confused.
This is like 8 times shots of the process in the plane. So
okay, that was my question.
So and what about the recovered ones? Are they're not marked, or
they're not shown? Yeah.
Okay.
I removed those from the picture because they don't interact with any of the other particles after that. Okay, and this is sort of I guess a variant of another sort of class of models which sometimes have been called sort of A and B models, that encompasses several different other classes of models, and it's the same sort of rule, except we don't have the removing. So if an type A particle meets a type B particle, then the type A particle becomes of type B. And more generally, and so they'll all do independent random walks, but the type A particles and the type B particles might have different speeds. So the type, maybe the infected particles get a bit slower or something like that. And so now particles aren't being removed, and we just sort of have this growing disk of type B particles. And we want to understand the growth of that. Okay. And so Keston and Sidorevicius analyzed this in the case where dA equals dB, the speeds are the same, and showed that the sort of radius of this ball that is sort of growing linearly in time, sort of as you would expect. Although, of course, growing linearly in time means it's growing much faster than the random walks themselves are moving. A few years later, they proved a more precise result, which appears in the annals, where they showed that there's a shape theorem for this ball. So there's a convex symmetric shape U, a subset of the plane, such that sort of the location of the type B particles is sort of well approximated by T times U at time T. And so in particular, all the particles, all the type B particles are contained in a ball of 1 plus epsilon times T times U, and everything in a ball of radius 1 minus epsilon T times U is type B. Okay, and so this is kind of naturally what you'd expect. You sort of think that there should be, the infected particles on one side, the susceptible particles on the other, and sort of a front between them that should sort of, and the front should be moving along at some linear rate in time. And this is what will happen as long as the sort of location, the sort of what's happening around the front is, as long as there's a reasonable density of particles at the front, there's sort of, it's not passing through too sort of sparse a region. And so I think one of the main challenges that in their analysis was to show that essentially you don't get too many, that the front spends most of its time moving through sort of well-populated areas where there's lots of new particles to get infected, and so that the front can sort of keep moving along at a fast rate. And so just to give a very sort of high-level description of how they tackled that, if you look at the unlabeled particles, so forget about whether they're type A or type B, if the speeds are the same, then they just look like particles doing independent random walks. And so that remains in equilibrium for all time. And so you can show that areas where there's a lot fewer, the density of particles is much smaller than lambda, will be very rare, just by very simple estimates. And so there's of course sort of spatial independence. But if you look in time, of course, how many particles you have in one region at a particular time will affect how many particles there are at a later time. But not by too much. If these sort of red regions are indicating sort of the areas in space and time that are sort of very sparse on different scales, then they'll be contained on a bigger scale in a region where it's not so sparse, where you have close to the typical density of particles, and the diffusions of the random walks will mean that the densities will kind of smooth themselves out, and soon none of the local regions will be sparse anymore. And so so the density so the sort of sparse regions where the front would sort of move slowly through are very rare. They dissipate quickly, and so you can sort of push through an analysis that says that at least that the speed of the front will sort of keep moving along at a sort of fast linear rate. So the important thing here was that when we look at the unlabeled particles, everything is in equilibrium. But when the speeds of the particles are different, then you can't say that anymore, because the type A particles can be moving at different speeds from the type B particles. And so in this case, Keston and Sidorevicius were only able to show that the growth of the type B particles grows at least T over log T. and this is just because of the method of proof. You don't really expect any change qualitatively by saying that the one type of particle moves at a different speed than others. But to show that, we need sort of different tools for analyzing it. And so I mean, in principle, the labels of the particles and their locations could be dependent in some complicated way, but we don't expect that to be the case. And in particular, if the front between the type B and type A particles is moving at a linear speed, then it's moving much faster than the random walks, which only travel distance square root of t in time t. So it should be sort of rapidly moving and sort of keep finding new particles that are sort of independent of what's happened in the past. And we want to sort of make that heuristic into a proof, yes. And so to do this, I want to tell you about a related model called multi-particle DLA, which is sort of like what happens when you take the speed of the type B particles to be 0. Once they get infected, they just stop. And okay, so let me tell you about that. And it's sort of a variant of a more well-known model called diffusion limited aggregation. And here you have an aggregate of particles, and then which you can think of as the type B particles, and then you just add in one particle at a time coming from infinity until it hits the aggregate, and then it stops. And so this aggregate sort of spreads out over time. And you've probably seen simulations of this where you get, so the top picture is a large simulation of DLA, and you get this sort of very interesting fractal type pictures with sort of tree-like growth spreading out in different directions. And it's supposed to be a model of certain real phenomena. So the lower picture is electrodeposition in I think it's a copper sulfate solution. This is a sort of notoriously hard problem, and even some of the most basic questions you could ask remain open. And I certainly won't be making any progress on this model. So let me, but closer to the models I was talking about is what's called multi-particle DLA, where rather than having one particle come in from infinity and then hit the aggregate, we have a sea of type A particles that are all doing their own independent diffusions and or random walks until they hit the aggregate, and then they join onto it. And so this is like the case where the speed of the type B particles is 0, except I've put a sort of an asterisk there to indicate the fact that at least the way I initially specified it, it would be that a type A particle jumps onto a type B particle and then stops and becomes type B. If we defined it that way, then all the particles would just end up in the same spot. And so instead, we'll change the rule slightly, which is to say that the type A particle becomes type B just before it jumps onto the type A one, and then it gets frozen in place next to the type B particle. So that this sort of aggregate of type B particles is growing over time. Okay, and so here's a simulation of this by Alexander Stauffer. This is if you start with an initial density of, I think, 0.3 for the type A particles. And I don't know what the resolution looks like on your screens, but if you sort of zoom in, it has the sort of similar kind of tree-like structure that you see in the DLA model. But on a larger scale, it looks much more regular. And it looks like there's sort of some emerging shape theorem in the growth of the model here. So what we don't know that. We don't know the existence of a shape theorem for these models. What we do know is that if you have a high enough density of particles, then the speed at which the aggregate grows in time is linear. And there's two proofs of that, one by Siderovicius and Stauffer, and a different one by myself. And I'm going to tell you a little bit about both of those proofs and how we take different elements from them to tackle this more general AB model and the SIR model.
Could I ask you to distinguish between the usual DLA and this multi-particle? I didn't quite understand.
Yeah. So in the usual DLA, you have the aggregate, and then you start one particle sort of off at infinity. It does a sort of random walk until it hits the aggregate.
Yes.
Then you add in another particle at infinity and keep iterating this.
Yeah.
Here in the multi-particle one, you start off with some initial density of particles in the everywhere in the plane, and let them all do random walks simultaneously.
So it doesn't. The answer depends upon that density, or what?
So that's a good question. So how does the density affect the growth? And the conjecture is that in dimensions 2 and higher, there's no phase transition. So for any density, you just have a linear growth and the shape and convergence to some shape theorem. On the other hand, if the density is really small, initially it will look a lot like the regular DLA process.
Yeah.
But that's just sort of a transitory effect, and that if you run things for time for long enough, that it will eventually the shape will become more and more uniform. So I think if we could prove more about the original DLA process, we could prove that there's no phase transition. So in a sense, if we could prove more about the original DLA process, we could prove that multi-particle DLA does not behave like DLA. But since the regular DLA process is so difficult, we haven't been able to do something like that yet.
Thank you.
When you say that this growth is linear, but you don't know the shape, so what is it? The diameter is growing? What do you know that's growing?
Yeah. So what we really know is that say the diameter is growing linearly in time. Siderovicius and Stauffer's proof says a bit more, which I guess is that everything, all of the particles within a ball of radius at constant times t have been absorbed by time t, with probability tending to 1.
So they aren't like in the other one. It seemed like the tree structure really had a lot of holes in it, right?
Yes. Here it will be sort of a constant density of the plane will get filled up. So it's quite different. In the original DLA, it's very fractal. Here it sort of only looks like that on a very small scale, but on bigger scales, you're just sort of filling everything up, really.
Okay, thanks.
Okay, so even the question in one dimension is not so simple, and so here it's just on the integers. We start with a sort of aggregate at the origin and particles doing a random walk on Z plus, and when so when a particle moves to jump onto the aggregate, instead it gets absorbed and becomes part of the aggregate. So I was a postdoc at Microsoft Research, so I'm loyal to Microsoft PowerPoint and making animations and things in that. But so this was sort of representing the one-dimensional process, and over time you get sort of a lower and lower density to the right of the aggregate. But in one dimension, there's only one thing you can ask, like there's no geometry anymore, it's just sort of a line segment. And so all you can ask is how fast it grows in time t, and how is that affected by the density lambda. And sort of surprisingly, actually, only in dimension one do you get a phase transition in lambda. It's usually the other way around. But so Keston and Sidoricius in a different paper from 2008 showed that when lambda is less than 1, you get growth like square root of t, and this just comes from the fact that you need at least for it to grow by at least length L, you need at least L particles there. And initially you only have lambda times L particles, so you have to wait long enough for more particles to come in. And since they're like random walks and they only travel distance square root of t in time t, then it's only going to grow by sort of length square root of t. I showed the other direction, that when lambda is greater than 1, xt over t converges to some positive constant, c. And essentially what happens is that the aggregate's moving along sort of at some constant rate. If the sort of infinitesimal jump rate slows down too much, then there's a sort of mean reverting process that sort of pushes it back up. And there's a sort of multi-scale, so you can give a multi-scale argument to show that it doesn't get too slow. And this combined with the renewal process argument gives the sort of almost sure convergence. But surprisingly, it also gives you a bound in higher dimensions as well. So you can, if you look at the sort of rightmost particle in, say, 2 dimensions, you can stochastically dominate that from below by the sort of rightmost particle in the aggregate in 1 dimension. So it grows.
I understand. Sorry, I'm just like learning this as we go along. When you're not transient, when you are transient, then in the one ball model, I'd assume there's a fundamental difference in dimension, right? No? I mean, you got these guys. So I mean, the minute in 1 and 2 dimensions you visit everybody with probability 1. Is that not relevant?
It doesn't end up really playing a role here, because essentially you have a density of particles everywhere. So the sort of
yeah, that's in this multi guy, but I asked in the ADL, whatever.
Oh, in the original one, yeah, then you have to be more careful how you define it in the for the original model. But
you would imagine there that the thing is very sparse. I don't know. Or if you went to a tree, for example, it would become extremely sparse. Yeah.
Yeah. Well,
anyway, this was when I asked you at the beginning. Was there a reason? I guess this is a geometry problem for any graph. I guess, right? For any infinite graph, that's the kind of the infinite setting.
Sure. Yeah. So,
and I guess I was wondering about a pandemic, why it's Z, or Z cross Z. But I guess that is a reasonable model.
I mean, in a sense, well, I mean, in a sense, we live on, we walk around on a 2-dimensional surface, although, of course, we have a lot more random connections a lot further. So,
and do you know if that would, do you know that impacts this kind of problem?
I think once you start adding in sort of long-range random edges, then it starts to spread very quickly, as you would expect. Yeah, as we've observed. Yeah. So in let's say in dimension 2, though, you can sort of stochastically dominate how quickly it moves, say, in the x coordinate by the one-dimensional process in this multi-particle DLA, and show that when lambda is greater than 1, it sort of grows at a linear speed. And you can sort of tweak that argument a bit and get something even a bit better. And I know the first sort of order approximation says you can get sort of linear speed even when lambda is bigger than 5/6, say. So a density slightly smaller than 1. Okay. Let me also mention the critical case, because this was something that Dor and Danny and I finished recently. So in the critical case, in one dimension, it grows like t to the 2/3. And if you take the length of the aggregate, rescale by t to the -2/3, it converges. The process converges to an integral of a diffusion process, where the diffusion RT satisfies the stochastic differential equation dRT equals 2RT to the 5/2 dBt, and B is Brownian motion here. So this was kind of a surprise. I mean, I think most projects I work on, I sort of know what the right theorem should be, and it's just usually a matter of not being able to prove it. But here, this was something that we discovered in the analysis along the way, so that was fun. The process RT is -1/3 self-similar, so it satisfies the following scaling relation. And something I really should have known but didn't know before this was that if you have a self-similar diffusion, then it's a power of a Bessel process. And a Bessel process, so a d-dimensional Bessel process is just like the distance from the origin of d-dimensional Brownian motion. And so our process RT is like a Bessel 8/3, and there's a natural way of extending Bessel processes to non-integer dimensions. So Bessel 8/3 to the power of -2/3. And so in a sense, we should have been able to guess this from the self-similarity, but I don't know, we didn't. But it just sort of emerged from the calculations. We don't really have a good explanation for why the dimension is 8/3 in the formula here. If it was some different dimension, then there'd be an extra term in the stochastic differential equation, which would be like plus a constant times RT to the power of 4 dt, so a sort of a drift term. But it turns out the dimension 8/3 is exactly what makes the constant in the drift term 0. And so it makes RT a local martingale. It's not a martingale, but it's a local martingale, because it tends to 0, actually. So that's the critical case. I want to tell you about one sort of tool that's used in both the supercritical and the critical case. I won't tell you more details because, well, the critical paper was 130 pages long, so there's a lot more going on. But and the idea is we want to look at the density of the particles conditioned on the history of the aggregate. So if we look at the history of xt, how many particles are there sitting right in front of the aggregate at time t? And it turns out that conditionally, it's still Poisson. And the reason for this is if we think of which particles are sitting right in front of the aggregate, they're particles whose trajectory has meant that they've avoided the aggregate up to that point. And now if we think of the initial Poisson density as not just being a Poisson process over initial locations, but a Poisson process over initial locations and future trajectories, so a Poisson process over some kind of path space, then we're just looking at the measure over paths that end right next to the aggregate and avoid the aggregate between time 0 and time t. So if we write yt as the time reversed version of xt, we can write down sort of a formula for the density of particles in front of the aggregate at time t. And this gives us the infinitesimal speed of the process at time t. So it's given by lambda over 2 times the probability that this time reversed version of xt is greater than or equal to an independent random walk given the history of the process. So it's a conditional probability, so it's a random variable, and sort of analyzing how this speed evolves over time, then you can sort of analyze how the aggregate grows. In the supercritical case, there's a sort of mean reverting process where if the speed gets too small, it speeds up again. In the critical case, it behaves like a sort of diffusive process, and you can couple it to a continuous time branching process that sort of just emerges from the calculation, and understand the diffusive behavior of that. But the main idea from this that I want you to take away is that if we just sort of look at the aggregate, conditional on that and its history, what's in front of the aggregate is still Poisson, but it's a Poisson with a different mean, but a mean that we can sort of understand. And so this is one of the ingredients that's sort of important for us in looking at these AB models. Okay, and the other one will be looking at using the proof of Siderovicius and Stauffer. So they considered a slightly different model. Rather than having Poisson number of particles at each vertex, they just have at most one particle, and then the particles do an exclusion process. So it's like a random walk, except if they want to take a jump to an already occupied site, then that's blocked. And they do it with an initial density, which is 1 minus epsilon for some small value of epsilon. And so because epsilon is small, there's just very occasional holes where there are no particles. And they do a sort of multi-scale analysis to say that as the aggregate is growing, when it encounters one of these holes, it sort of quickly surrounds the hole and keeps moving on. So I stole this picture from their paper, and so the sort of small white circles are the holes, the black disk is the aggregate, and as it grows, you get these sort of yellow sort of cutout regions, which are where it sort of encountered a hole. So there were no particles there, so it didn't grow in that region, but in a short amount of time, it manages to sort of surround that and sort of keep moving in that direction. But sometimes you run into bigger collections of holes, although those are much rarer, and you have to show that it can sort of keep surrounding those as well and keep moving at a good speed. And so the way they do this is they introduce what's called, or what they call, first passage percolation in a hostile environment. So this is sort of we start off with a single red particle, and then it grows according to sort of the normal rules of first passage percolation. So it spreads to neighboring blocks at rate 1. But then there's the hostile environment, which are these blue seeds, and there's a small rate epsilon density of them, and they don't start growing until the red particles try and jump on them. And when the red ones try and spread to a blue site, then the blue site can start growing. And they grow also according to first passage percolation, but at a slower rate, sort of some theta that's less than 1. And so then there's a race on, both a sort of competing red and blue particles, but the red ones move faster, so they have a good chance of being able to surround the blue ones, although it's random, so it's possible that it happens the other way around. And so you want to ask, does most of the plane get filled up with the red particles? And they show that if epsilon is small enough, then that indeed happens with positive probability. There's of course a probability that it fails straight away if the red particle is just surrounded by blue ones at time 0. Okay, and so we make use of this construction. So actually, sorry, maybe let me tell you how they use this first. They what they show is that the aggregate in their multi-particle DLA process you can couple it with this first passage percolation model such that the aggregate contains all of the red sites. So it's so if this one grows linearly, then so does the multi-particle DLA. Okay, so we also make use of this first passage percolation variant, although with a slightly simplified set of rules that I think make it a bit easier to analyze. So again, we'll have a density epsilon of these blue seeds, but now the blue particles will spread at a deterministic rate. Just if they'll take exactly time 1 to spread to their neighbors. So there's no randomness in the spread of the blue ones anymore. The red ones will still spread randomly, but they'll have a maximum spread time of delta. So they move considerably faster than the blue ones. And then, and what we can do is just draw a bubble around each of the blue particles. And if there was only one of these blue seeds, then the red would be able to spread to everything except what's in the bubble. But if there's 2 blue seeds that are close to each other, that might make it harder for the red to spread. So we might need to surround them by bigger bubbles. And maybe even these second scale bubbles are too close to each other. So we might need to put them in an even bigger bubble. And so there's a sort of, so you do this on a series of scales. And what you can show is that if the initial density of blue seeds was small enough, then most of the plane is not in any, is in the complement of all the bubbles. And if the initial red location is outside of any of the bubbles, then it will eventually spread to contain everything, every site that's not in one of the bubbles. So you'll contain, so most of the plane will end up being red.
So let me make, can I just interrupt for a second? Is this a construction you're using, or an analysis you're using for the one-dimensional case?
No, not for the one-dimensional case. For
Okay.
dimensions.
So what is this? What is this for? Or is this something separate?
This was what Siderovicius and Stauffer used in 2 dimensions.
Okay.
Although they had a slightly more complicated version of this. And this is also what we'll use to analyze the A-B model and the SIR model.
Okay.
You're now explaining the 2 proofs of the linear growth.
Yeah. So this is.
Yeah, that's what I wanted to understand.
Yeah, I also was confused about that. You jumped from 1 to 2 dimensions.
Yeah, that was my problem too.
Yeah, so this is proof 2, and now we want to sort of combine elements of those to show the growth of the or the AB model. Okay, and so we want to use like something from the first proof, which was essentially to just say, let's not observe everything. Let's just observe the areas that have infected particles in them. So we'll sort of allow the process to evolve, and we'll only sort of shade certain boxes once infected particles, once there's been an infected particle in it, and we'll only look at what's happening in the shaded boxes. So we either shade them red the first time an infected particle enters them, or if, and I should have said the side lengths will be L, or if an unshaded block has been sitting next to a shaded block for at least time L squared, then we'll shade those ones too, so that the sort of shaded region grows will keep growing at a certain rate. It will grow by at least sort of 1 block every L squared time. And so we're sort of only going to be observing particles that have been in one of these shaded blocks at some point in time. So let me just give you a sort of slower version of that. So in the first step, well, no infected particles left the initial block, but 1 particle infected another one. Then here, the particle infects a neighbor, or enters, an infected particle enters a neighboring block. And so then we reveal what's happening in that block. And so the question is now, what do we see when we reveal it? And approximately what I'd like to say, okay, what would be nice is if what we saw in that new block was just an independent Poisson process. And if that were the case, then what I would do is I would construct some initial Poisson process, which is what's on the right. And then when a new block gets revealed, I'll just take the corresponding block, and then there's 1 particle there, and I'll map that across to the picture on the left. And then when, so a couple of new blocks get revealed, I take the corresponding particles in those blocks on the right, and then they get revealed in the picture on the left. And we sort of keep revealing things like that. And then these 2 blue ones, they were next to shaded blocks for too long, so they also get revealed and shaded blue. And we sort of reveal the particles in them based on this initial Poisson process we have on the right. So this is not quite the right thing to do, because when the first time an infection enters a new block, and the first time you look at what's happening inside that block, you shouldn't see just a sort of rate lambda Poisson process there, because that's not taking into account the fact that some of the particles there may have been in sort of the shaded region before that. So you need to sort of only reveal what particles should be there if they were never in the shaded region beforehand. So let me give you another sort of picture, hopefully describing that. So now in this picture, this is just going to be so space is just on the x-axis, so each column represents a block, and time is in the y-axis. And so imagine at time t, this block is revealed. And so we have to decide what particles are going to appear in that block. So what I'd like to do is sort of say at time 0, we just generated a point process in that block. There's 4 points. I'll put those points in this in the block, and then let things evolve from there. But that's wrong, because we should only have particles that have avoided the shaded region. So what I need to do is draw the shaded region on the right, draw sort of past trajectories for each of those particles, and then remove any of the particles whose trajectories in the past took them through a shaded region. So get rid of 2 of them and keep these other 2. And then we place these particles in our process, and then keep running along from there. And we'll use the sort of future trajectories of them to decide to sort of say what those particles are going to do from now on. And so why have a complicated construction like this? The idea is that we want to be able to sort of, for each block, just kind of decide what particles will be there at the very beginning of when it's revealed, but make that decision at the very beginning of the process so that it's independent of the decisions we made for all of the other blocks. And this way we can retain a lot more independence of the process than we otherwise would. But we need to do this sort of elimination of particles that have sort of trajectories going through the shaded region to take into account sort of actual dependencies in the distribution. Okay. And so what do we get from being able to do this? Well, we get to be able to define what are the which blocks are going to be bad. And so these will be like the blue seeds in the first passage percolation in a hostile environment problem. And so what's a blue seed? Well, I'll tell you what makes a block not a blue seed, which is that when an infection first enters the block, regardless of where it enters, a lot of particles will get infected by time delta squared and spread infections to all the neighboring blocks, which is what we want in terms of, this block gets infected and quickly it infects the neighbors. So how can we guarantee that there are any particles there? Well, we need to check that there are particles whose past trajectories miss all of the shaded regions. And there's a maximum sort of that the shaded region can be, because if this block is revealed at time t, then, and another block is at distance k blocks away, then that block can have only been shaded for time k times L squared, because the shaded regions grow by at least one block every L squared time. So the particles will have at least a constant probability of avoiding all the shaded regions. So we'll add, in a typical block, we'll be adding a lot of particles, and they have a good chance of quickly hitting the infected particle that entered, and then spreading the infection to their neighbors. And by taking the side length L to be large enough, we can make the probability of something being a bad blue seed to be as small as we like. And then through the proof, we can show that there's sort of the set of blocks that have that get infected grows linearly. So there's lots of type B particles around everywhere, and they'll quickly infect all the type A particles. And so the final sort of theorem is that if the speeds of both types are positive, then you do get sort of a linear growth in the sort of region of type B probability particles with high probability. Sort of the open problem is, can we establish a shape theorem for that? That's sort of tricky because we don't have sort of monotonicity in this model. So in a sense, adding extra particles can potentially slow down the growth of the process. And in the case of the SIR model, we show that there's a constant probability that the infection survives forever as long as the recovery rate is small enough. It's only we don't show it with probability 1 because there's a probability that the infection just dies out straight away. And in fact, the first time I did these simulations, that's exactly what happened. So since I didn't want to just show a slide of just all black dots, I did the simulation again. But as you let the recovery rate tend to 0, the probability of the infection surviving forever tends to 1. And also, in any particular point in space, once the sort of wave of infections has passed through there, the time at which then after just a short time, like it should be log t, but certainly t to the little o of 1, you don't, after that, you don't see any more infected particles there anymore. So there's just sort of one wave that washes through, and then you don't see any infections again. And what's left in the middle? Well, there's a low density of particles that manage to sort of, I guess, socially distance properly and avoid all of the infected particles. And so you get a low density of susceptible particles in the middle and no infected particles. And sort of because the density of the susceptible particles is so low, they're essentially in a herd immunity regime. Yeah, and I guess that's where I'll finish off. So thanks for listening.
Thank you very much.
What does the shape look like in your simulations? I didn't quite get it.
It was so, I mean, it should be some, convex symmetric body, but it's probably not a circle. It probably depends on the lattice in some way. Here in this picture, I obviously haven't run the simulation long enough for that to happen, because it's looking a bit concave in in the top right hand side. But that, I mean, as n tends to infinity, you would expect it to become sort of symmetric in both the y and x axis and convex. To get sort of a herd immunity picture that sort of matched the theorem took quite a bit of tuning the parameters. If you take the recovery rate to be too high, then the process does the process grows, or like the infection sort of will die out. But if you take it to be too small, then the infection is just too efficient, and almost everything gets infected. So the fraction of particles that sort of survive and get into the middle becomes like, it's still positive, but a rather small constant. So it took quite a bit of tuning to get something that actually looked like it had a herd immunity regime here. But that's the drawback of a sort of simulating something for a finite n when your theorem is as n goes to infinity.
Those dots. Go ahead.
Oh, sorry, Tom. So in the theorems that are proved where you have actually a shape, does the proof actually determine the shape too, or
no? The shape just comes from sort of like a sub-additivity kind of.
So just abstract, some abstract argument. I mean, like some abstract reason. And is there any path to actually getting a hold on what this shape is, or is it just?
No, this is a very hard problem, and so something like first passage percolation is a much simpler question. That there it's rather easier to prove the existence of a shape theorem, but basically so in first passage percolation, you can have passage times that have whatever distribution you like, and let's say it was a continuous distribution, and you always expect to have a nice shape with positive curvature everywhere, and that's, no one's been able to prove that it doesn't look weird and with facets and
Is the shape a scale of a fixed, compact, convex, weird set, or is it the shape much more complicated?
I mean, the shape theorem should just be, you have some, so compact, convex, symmetric set.
There's a stabilizing set whose boundary may be convex, but it may be nowhere differentiable or something.
So so that's right. We don't know that it doesn't have flat edges. We don't know that it's sort of nice and like positive curvature in everywhere. yeah, and there's a lot of things in first passage percolation that you'd be able to prove if you could say that the shape behaves nicely, which we can't. And for these particle systems, it seems even harder to be able to say to determine the shape exactly, or even say properties about like the boundary of the shape.
And in your proof, when you get the diameter, I didn't see how you control is it the diameter, or you're controlling much more?
So essentially, in the SIR model, say we're showing that the region where the infection has spread through like contains a ball of radius, a constant times t, and it is also contained in a bigger ball of another constant times t.
Sorry, what does SIR stand for?
This was susceptible, infected, removed. So this is sort of the epidemiology terminology that sort of people from particle systems have stolen.
Thanks, Greg.
So the points inside, the dark points inside that region, that you have there. So those are guys that they've never been infected, right? They've just never been infected. So it's just that the red particles are not going to go back to infect them, I suppose. Right.
So
I mean they could though, right?
They could, but I mean, the red particles only stay red for a constant amount of time on average, whereas this is, the radius is growing with time. So actually, once a region has had a red particle in it, then we show after a relatively short period of time, it will never again have a red particle. So, I mean, the truth should be like after an additional log t amount of time. But I think our proof is sort of some.
So it's not as if they have immunity. It's just they've never gotten infected for reasons of luck or somehow.
Yeah. So I mean, you see there are points around the boundary where there's sort of kind of gaps in the infected particles that they can sort of sneak through occasionally, and just a constant density of particles managed to sort of sneak through and avoid all the infected ones. And then once they've managed to sort of survive the wave for a short amount of time, then there won't be any more infected particles around there, and then they'll survive forever. Because the density of remaining susceptible particles is too low to sustain an infection after that. So it's really what you think about in terms of herd immunity in epidemics.
So it is now there's presumably a transition as you vary mu, right?
Yeah. So we don't. I mean,
and that's too hard, I suppose, to get to do what you did in one dimension.
Yeah. No, I mean, really, our proof is probably only working for sort of very small values of mu, the recovery rate. And yeah, so we don't.
But I mean, if you run it numerically, you'll see a transition, I guess, right?
Yeah. And it's it probably, if you doubled mu, then from the one that was used to generate this picture, then it would be, I think the infection would die out at that point. So it's, so I mean, I tried various simulations to get sort of the best picture for this slide. So.
Any more questions? Okay, so if that is not the case, thank you, Allan, again.
Oh, well, thank you. nice to see everyone.
Well, hopefully we'll see each other in person.
Hopefully soon. Yeah.
Yeah, hopefully soon.
When the wave moves away.
Yeah. Yeah.
Well,
I don't want to say which ones we are here.
you guys have been vaccinated,
sorry,
right?
I do have a question. Is this at all real? I mean, are the epidemiologists, that's probably how you say it, is this a model that they have any interest in?
I mean, not on the plane like this, because people's interactions are more mean field, I guess.
And so there are models there that people.
But the SIR model is a real epidemiological model, but you would sort of look at it on the graph of social interactions that people have, which is more like
sort of a big graph.
There's some spatial geometry to it, because you're more likely to interact with people in your neighborhood and city, but there's also sort of a lot more long range edges.
And what's the theory there? Have you looked at literature there? You see what people, I assume there's a tremendous amount of research into that now.
Yeah, I mean, yeah, so I mean on either the mean field model where everyone can affect everyone else, or on random graphs, you can say in sort of a lot of detail what happens and then on sort of other graphs where there's sort of enough connections, then you can sort of say that it spreads very quickly. On a general graph, you're not going to be able to calculate exactly what the thresholds are, but I mean, there are lots of qualitative things you can prove.
Right.
Yeah. Well,
Thanks.
have a good afternoon.
Okay. Guys, you have been vaccinated, right?
Yeah, well, I'm getting my second one.
Yeah.
You're getting your second one. Okay. Peter?
Oh,
I have
had one shot. Yeah. I told
you.
Oh, I got two.
You got two. Did you get the Moderna, Peter?
Where?
The Moderna shot, or did you get
Yes.
And did you have a reaction on the second one or not?
Some, but not enormous. I just felt really tired for a day or two. So.
Well, that's yeah. I had nothing.
Listen, it beats getting the disease.
Oh yeah.
Yeah, I guess by far.
By far.
I didn't hear anybody, or at least last time I read, there's no case of somebody seriously impacted by the vaccine, by the vaccination, right? I mean, there's like with millions of people who already have taken the shock is quite remarkable, I would say.
It is remarkable.
Oh yeah.
Right.
Yeah.
But I think there are some cases where
suspicious almost.
I think Alan wants to make you feel less comfortable. Yeah?
Oh,
yes.
Like people who have like allergic reactions can sometimes need like to take the epidural.
Yeah.
Yeah. So.
Yeah, okay, but allergic reactions, of course, okay, that's I would say a different story, right? I mean,
sure,
like really like people impacted for some weird reason, they are going to have like a strange reaction to it, which is not. No, I mean, allergic reaction, I guess, is not something you can really avoid. No, I mean.
Yeah, I mean.
Yeah, there's always going to be some, I guess.
There's always going to be somebody who's allergic to something. I mean, that sounds almost impossible then.
Anyway,
well, as a friend of mine was joking, anyway, the whole point of the vaccine is to have an allergic reaction, essentially. No? That's a controlled allergic reaction, more or less. What were you saying, Peter?
No, I emailed you. You got my email.
You emailed me. No, I don't know. No, did you?
About a meeting. Yeah, well, okay. We don't need to discuss it in public.
Yeah. I see an email from Peter Sarna.
Okay,
yes,
I'm leaving.
Yes.
You guys. Nice
Take care. Yeah.
Thanks.
Bye-bye. Have a nice evening.
You too.
See you.